Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. Alright, so in the last episode we started with the Dixon method. We implemented the first part and were able to find b plus 1 relations or b smooth values. Now we are going to talk about the metrics and how to extract the solution out of it. We're going to use the Gaussian elimination for that. It will have several improvements over the regular Gaussian elimination. Since we are working on a base 2 space, we are going to use XOR instead of multiplications. And we are also going to use bits instead of numbers, integers. We are going to remove any relation that doesn't have more than one prime. So basically, if it only has one prime as one of its columns, it will not be possible to eliminate. So we will filter those out. The algorithm works as follows. First, we start by filtering out all the columns that has only one prime. Then we build an identity solution matrix with the size of row count times row count. So each time when we are XORing or eliminating rows, we are going to XOR the solution matrix. It will allow us to extract the solution once we find the null space or empty or zero rows. Cool. We start by iterating over the ice vector in our factor base bounded by the constant b. We're iterating over all the remaining rows. We find the first row with I prime and we are mark it as eliminator. We're using it to eliminate all the other rows that have I primes. And then to not return this I prime to other rows, we mark this row in some special way, so we will not use it as an eliminator in the future. We can, however, use other rows to eliminate other primes inside those eliminators. Now, I don't know how efficient was my explanation of this algorithm, so I prepared an example to kind of try and illustrate it. It's a more complex example than the one we saw in week yesterday. It will go over the entire matrix. So let's assume that those are our B-smooth values. It's not corresponding to any real number. I just made those up. But it will serve a good purpose for this example. So 2 power 8 translates to 0 because 8 is an even number. 3 power 3 is 1 because 3 is an odd number. Same as 1, 2, 2, 5 translates to this vector. Similarly to other vectors, and we get this matrix. Now you see how 11 is times 3 is the only odd value, the only value that has 1 in this column. So we will not be able to eliminate it by any other value. So we are filtering it out. So row number 2 is going to be removed. Now we start the Gaussian elimination. So we find the first row that has 1 as the first value. It's this row. I mark it with a minus, and then we eliminate all the other rows that has 1 as the first value. So it will be those 2 rows. So I'm XORing that with that, and it gives us this and this. And this is the solution matrix. We're starting with identity matrix. look how here it's 6 by 7 rows. In here, it's the number of rows, so it's 7 by 7. So when we are xoring those two rows, we are adding 1 in here. So now, if that row is going to be a solution, I know that it's made of those two rows, right? And if it's going to be XORed again later on, and one of those value will disappear, it means that one of those rows been used twice. And if it's been used twice, then it's already a square, and we don't need it as part of our solution. Cool. So moving forward, we are moving to the next value. We are marking this row to not be used again in the future with that sign. Then we are searching for 1 on the as the second value. It gives us this row, so we're using it as eliminator. Searching for all the other rows that has 1 as the second value. We found those two. We are eliminating, and we get that. Moving forward, 1 as the third row. We found 2 rows to eliminate. We're getting that. We have now looking on the fourth row. This is the one that we are being looking for. And here we were supposed to look at this column, but it's 0, so we are moving to the last one, which is that. I didn't use this one because it's marked as reserved. And so now from here, we can see two solutions. We can see this row full of zeros and this row full of zeros. From the solution matrix, it means that we have a index 0, 1, 2, and 4 as our solutions. And for the last 0 rows, it's 0, 1, 3, 5, 6 as a solution. So that is the original vectors that we had. And so for the solution 0, 1, 2 will include the first row, the second row, and it's supposed to be the second, but the second was filtered out. So it's actually corresponding to the third and the fifth row. And indeed, you can see that when you're multiplying those, so we are getting 2 power 16, 3 power 16, and it's a square. It's that power 2. Awesome. So this is the algorithm. I hope that the example is clear. And now let's jump into writing it down. Now it's quite a big class, so I want to create a new class for it. Yeah. Cool. Let's put it into a matrix bucket. Cool. So that will now that should get an input as the B smooth value. So we need to extract it to its standalone class as well. Like that. It's much easier outside the presentation mode. And let's move it into. I wanted to move it into another package. Yeah, I want to put it in a data package. Cool. Right, so we have our B smooth, and it's going to be the input for a Gaussian elimination matrix. Solve. And it's going to return solutions of same type. Now, because it's relatively a complex implementation, let's create a unit test for it and work with our example. So let's do a setup. Let's work on a solve. Right. So we are working on the first 7 primes. Let's create the vector base first. A prime private primes. Going to be 2, 3, 5, 7, 11, 13. Yeah, those are our primes. And now for the setup, for solving, new elimination matrix, solve. Then I want to give it the list. So smooth list. Let's make this list in the setup. So during the setup, list. Let's actually start with something simpler. And do the smooth equals to something, and then list equals to arrays. Now we need to make that. So let's provide the powers and calculate that based on the powers, the vector based on the powers. So we move, and we'll give it the powers, which is 8, 3, 1, 2, 2, 5, 2, 2, 5. So going to be powers. We are returning a new bismuth value. So for A, it doesn't really matter. We are, for that example, we are not using the real value. For B, we want to calculate the actual number. So let's call it B and the vector. So it's going to eventually build the multiplications for all the primes. So let's start filling it out. So have primes. Index loop. and powers I. This is the power that we are multiplying each of the primes. So prime, so b is equal to b. Actually, we can do just power. B multiply prime for that value. Yeah, we don't need this. And for the vector, it set the i's prime to the powers I. If it's not 2 equals to 0, and set it to true. All right. And now let's test that we got the input right. So in here, before solving, let's do some printing. Print vectors and give it the prime. So it has access to the prime list. Okay, so smooth list. Going to print each value. So we start with the powers. Oh, but they are now inside B. Okay, so what we can do is iterate over the primes and do system print subtract power from B, and we're extracting the power from that value using that prime. And let's print a space. And then we want to print, let's separate them. And we want to print the vector. So speed smooth vector get I. So if it's true, we want to print 0, and otherwise want to print 1 for all the odd values. And finally, system line. Okay, and for this one, fact power, so it will return an integer on the prime. So count equals 0, return count, and while b mod prime is equals to 0, we'll do count plus plus, and b equals to b divided by a prime. Right. So that should print that list. Let me fully fill it. Okay, I filled the rest of the items. Let's run it. Okay, and I verified that this indeed was our input. So we got the first part correct. Awesome. Now for the second part, let's actually see that the solution that we are getting here is indeed the two solutions that we got. So we need actually to have a list of those. Solutions. Now, insert in equals. Come on. Very nice. Insert equals. The expected value is 2, and the solution size should be 2. Then assert after that. The first solution should be the product of that. So it's 16, 16, 8, 8. Okay. And 20. So the solution got 0. So the product of that should be equal to the product of that. Yeah, let's implement those two methods. Return a big show. I've already had something similar, but not quite the same. We're taking including big integer b equals 1 and b equals b multiplied by primes at I powers I. So that value should be equal to the values that we found here. So big integer b equals 1 and be smooth b equals b multiply by b smooth. Okay. All right. First one and the second one is 1812. All right, so we got our unit test set up. It should fail now because we haven't implemented anything. Awesome. So now let's finally get into solving our algorithms. Can be very optimistic about what is ahead of us. So this is what we want to return. Solutions for new solutions. Almost done. Awesome. Now we want to filter that list from any value that it's smaller. So equal to filter single primes. Okay, done. And then we want to iterate over our prime base. So that part is missing here. So let's add it. Edit integer prime base. We want, and let's fix that. So the prime base here will be those values, primes. So arrays primes. Cool. Right. So this method needs both to filter the primes and also create a copy of that list, because we don't want to modify the input. Cool. Now we are working on prime base, iterating over each prime, right? So where's our algorithm? So filter out, done. Now iterate over each item. Oh, sorry, build an identity solution matrix first. So it's going to be matrix. Let's also use a list of bitset solution matrix build solution matrix. We'll need just the Bismuth list, even just the count, but it's an identity. Okay, so we got that part done. And now we need to iterate over each prime in the prime base up to b, which is the size of prime base. So yeah, that's what we're doing here. And during each iteration, find the eliminator. So this is going to be our eliminator. Okay, and we need to find it inside our list. List to find eliminator inside the list. And if we indeed found it, then we need to make sure that we are not using it again. So we need to save it. So let's use a set for it. Set of, we are finding the eliminator inside the list. We also need to provide the prime index. Right. So it could be a set of integers, I guess, where each integer is corresponding to the index of the prime set. So that will be eliminators. A new hash set. Yeah, that works. And when we are finding the eliminator, we need to make sure that we are not taking one from the eliminators. So let's do that as well. And once we found the eliminator, then we need to eliminate using the eliminator, using the solution matrix, and using the Bismuth list. What is it? Oh yeah, weird to not use the input. Cool. So we eliminated after we eliminated the list, we are basically done. And now we need to extract the solutions. So we're going to work on, we need to check what rows are now empty inside the bsmooth list. So if bsmooth vector is empty, then it's been eliminated and it's a solution. So we need to take it out from the solution matrix, just like we did here. So we saw that that row is empty, and we took that row from the solution matrix. So solutions and extract solution from solution matrix using this vector. I think it will be easier to work with indexes. So we'll use the index. So the solution matrix, the bsmooth list, and the index. Index. All right, and that's it. Now we just need to implement it, right? Cool. Filter primes. So for filtering primes, we need to make sure that we have at least 2 primes of each item. Let's use a map of a prime index. So it will be an integer with a count. Smooth, only need to get the ones. Do we have something convenient to give us that? Next edit. No, we need to iterate over our prime base. So filter single primes, we need the prime base as well. So for prime base, if we smooth vector get I set to false, then map put in the index I. And the keys that we want to get is map get I starting from 0 plus 1. Then we want to, so this is for all the values. And then if you only have, in our map, we only have a 1 for one of those items, we want to get out and remove that index. So we are missing the index information of what value from the list we want to remove. So when we are inserting item in here, we really need to place the index. So we can do a trick and say that the index will always be negative at first, and once we get it for the second time, we'll turn it to positive. So that index value will correspond with the location inside the list. If map get I. Okay. So if there is nothing, if the previous index equals to null, then we will just insert a negative value minus I. Otherwise, integer is already negative, and we'll make it into positive. It really doesn't matter that index because we only care about the negative indexes. And else we don't care, because if it's already positive and there is more than one of those, we simply don't care. So now we can iterate over the map values and if the value is smaller than 0, then we want to remove it from the Bismuth list. So this is our original list. We want to clone it. So our list will be a clone of that. We will not affect the original list. And now we want to remove it from this list. So if I just do that, remove value, it won't be a good solution because this value will affect the other indexes. So we need those values to be ordered. So let's do that first. Indexes to remove. Now we can iterate over indexes to remove. And remove all the indexes. Let's sort it first. Let's sort it from small to large. Now we can safely say that it's not least remove not I, but indexes to remove I. And that should be all right. Hopefully that will do the work. Sorry, return on. Right. This is the list that we are working with. Yeah. Hope that will do the job. Solution metrics. Build solution metrics. So now we need to build size. It will be the row and column. And we will have List of type solution matrix. Okay, and solution matrix and new bitset. But that bitset only need to have one item set, which is take set row to false. Right, get row and set it false. False is 1. So it will be for row 0, we are setting 0. For row 1, we are setting 1. So, solution matrix. That right is as well. Find the eliminator. So we have already filtered Bismuth list. We are sorting for that index for eliminators. It would be nice to know what is the prime set, maybe. I'm not sure. It's just the index of the prime. I don't really care what prime is it. So in the Bismuth list, where we're sorting, we want us to ask the question if Bismuth vector get I, if it's equal to false, which is 1. So if it's set, then we want to use it, unless it's already been added to the eliminators. So the eliminators needs to be of that value. Eliminators. What did I do? Okay. Okay. So we are first checking if it's set, and then if you're trying to add it and it's already in there, it will return false. But if you successfully edit it there, then it's a valid eliminator and we can just return it. So this is the eliminator. And if you didn't find it, then we return null. Do we take care of nulls? So if we didn't find it, there is nothing to eliminate, and continue with the next row. Otherwise, go and eliminate. So this is our Bismuth list. Unless I'm eliminating myself, as Bismuth is equal to eliminator. If it's not, then I can eliminate. So Bismuth vector so eliminator. I like this magic. This is my favorite line in this entire algorithm. This is so fast. Yeah, it's just native XORs and it's represented with long integer, so this one is awesome. Also do it for the solution matrix. Get and the index that I want to eliminate. Oh, we don't have the index of the eliminator. So it's better to work with indexes here. So we can put it in the solution as well. So if bsmooth vector is not equal to bsmooth list get eliminator vector, and so call it eliminator, call it I for index, and this is eliminator. So bsmooth XOR eliminator. What's going on? Oh, I changed the vector. I wanted to change the variable. Yeah. Okay, and then solution matrix get I and XOR with eliminator. With not eliminator. We want to XOR two indexes, so that needs to be indexed as well. That's going to be a smooth index. That's going to be an eliminator index. Yeah, I think it's cleaner that way. So we are XORing the smooth index with eliminator index. Matrix get eliminator index. All right, XOR those two, and then that should eliminate. Now eliminator needs to be an index, so want it to be an integer. So it's -1, none is found, and otherwise it's going to be smooth index to be consistent. Smooth index. Yeah, something like that. So that's eliminator index. And it's an int equal to -1 that we want to ignore it. Otherwise, we want to eliminate. So once we eliminate it, we want to extract the solution, finally. So solution matrix, we want to, what is I? Yeah, I is not good name. I is the index of the row that it's an empty row. So it's a bsmooth index. I hope it's having the right context here. The solution matrix get bsmooth index. So this is the solution set. And we're going to return a bsmooth list solution. one solution. Return it. We'll fill it with I need the prime base. Yeah, we need to at least provide it with a prime base size. So it's the size of the prime base. Prime base size. We have an ISO. Yeah, so it will be inside our list. Okay, so now pset at I set and solution and we need to take the row. So bismuth list get I. This is it. Yeah. So now theoretically, our unit test should work perfectly. No, not a chance in the world, but let's see. Running the test. Okay. So it was expecting 2 solutions. It got 0 solutions. Let me fix this and see what went wrong. Okay, so one of the big mistakes that I made is treating zeros as positive and false as 0 as was 1. Yeah, so it needs to be changed. And another thing that I found is the filter single primes. The index here should be not the prime index, but the bismuth index. So let's start with that and then fix the other thing. So it's going to be bismuth index. Right? And then everywhere where I treated zeros true needs to be fixed. So go slowly. Yeah, that works properly. So I hope. Sorry, baby woke up. I had to switch rooms. So switching back to setting everything up. I think we fixed that part. Let's try it again. Oh, and another thing, it's the test itself. Yeah, when we are printing, so it's 1 for true and 0 for false. Makes much more sense. Then I power more 2 equals 1. Yeah, and let's see that we are printing it. Still right. yeah, that part still works. Cool. So let's continue and fix that. Let me find what's the issue now. Two problems that I found so far. Filter single primes. I forgot to replace the false with a true. And then filter eliminators. No. And then in eliminate, if B smooth method is not eliminator, and also if B smooth vector set in the smooth index. Let's try again. All right, a few more. Build solution matrix needs to be true. And then in the test, I missed a row. Let's try now. Okay. Okay, two things. Eliminate. So we can take it out. And then we need near the prime index. And we need to look at the prime index. Yeah. So eliminate, it will be I, the index that we are looking at. And then also, some solutions in the first result and returning here B right now. Okay, so we passed the first condition and we are still failing on the actual result. Progress. Okay, and now let's run it. Okay, let me check. Okay, had a few issues with the example itself. Forgot to eliminate that and that row, so I fixed that. I'll update the solution matrix as well. And also in here, we are filtering the list, and then when we're extracting the solution, we want to use that list unchanged. So let's clone it. So list. But that wouldn't be enough because the vectors will still change. So we need a deep copy. Deep copy. Let's work with lists. So return copy and with list and copy and with list. I don't like the clone method because we have problems with it. Well, we don't have problems with it, but it has sometimes problems. So I'll just implement a copy in here. Going to be smooth with A and B. those are immutable, and vector is not immutable. So vector, does it have clone? Yes, it does. Yeah, so native implementation of clone are fine. All right, let's try it. Okay, let's see what we're missing now. Stock solution. So we're replacing it with the original. Yeah, still a problem. All right, and in here, the stack solution, we need to look not on the prime base, but on the smooth that size. So we don't really need that. Now let's try it. And yeah, finally, it passed the test. It means that we have a matrix that can solve B-smooth lists and extract solutions, which is part of what we need to do. So now we can return to the previous episode and update it to use the metrics. So let's create a new one. New class episode type. Um, yeah, not sure about the name conversion of episode 5. Doesn't sound really good, but I want to make it easy to understand the episode. So, all right, and now after we found the B-smooth lengths, now we need to extract the solution. So new elimination matrix solve our B-smooth values. And it also need the prime base. So prime base, which we have in integer. Let's change it to big integer. So prime base. Just that. Don't know how that happened. Okay, so we are getting a solutions, solutions, but it's not it. We need to extract, to convert them into the factors of n. So for each solution, we need to do the multiplication to have the new a and b values. So let's call it a and b. And now we need to iterate over the solution. It says that a equals to smooth a multiply a and b equals to smooth b multiply b. Now we have we know that we have two values that we can add and extract the solution. I'm just not sure if one of them needs to be squared. How it's been created. So A is before we did the power on it. So we don't need to add power on A, and B, it's a smooth value that it's now becoming a square. So we need to take the square of B. So A add B square is maybe a solution. Maybe solution is not equal to n, and maybe solution is not equals to b 1, then log, oh yeah, maybe solution. Awesome. And we can return. All right, let's see if the combined effort works. We're tackling 70 bits. We found the B smooth, but we were able to extract any solution. Also log out. Maybe all of them were bad solutions. Also log out. Let's add the index. Say that will be I. Okay, let's try it again. It's pseudo random, so it's going to fail. Yeah, so we got 100 bad solutions. This sounds very unlikely, so let me check. All right, so here is the bug from previous episode. When we are checking for smooth, let's rename it to vector. We are resetting the vector over each iteration, which is not supposed to be. And also, another thing, can't really explain it. The key optimization doesn't work in this case. Yeah. So, removing it. I really don't know why, but when doing the key optimization, it's just not able to find valid results. Yeah. Let's try now. Oops. What did I miss? All right. So it was able to find it within the first solution. It found 47 solutions, and the first solution worked. All right. So now we have implemented successfully Dixon method. Next episode, we will talk about more meaningful optimizations to make this method much faster. It was long. I hope you bear with me until the last moment. I see you next time. Bye.